everyone to please settle down. Let's start. Okay. Good afternoon, all. I welcome you to the very first Perspectives lecture of this academic year on the topic Cosmology, the Story of Our Universe by Dr. Raghavan Rangarajan. Dr. Rangarajan is a professor of physics and dean of School of Arts and Sciences at Ahmedabad University. His areas of research are cosmology and particle physics, and he works on the processes that happened in the very first microsecond after the Big Bang. We welcome you, sir.
Thank you so much for inviting me to CEPT. I'm at the sister institution, neighboring institution to you, Ahmedabad University, and I'd like to invite all of you to come visit us also sometime. We have some very interesting talks and lectures that happen there, which might be of interest to you. Today I want to talk to you about cosmology. Cosmology is the branch of physics that studies the universe, its past, its present, as well as its future. So what do we know about our universe? As of now, using our telescopes and other instruments, when we look out at the night sky, what we discover is that there are lots of stars out there. They're grouped together in galaxies. The galaxies are grouped together into clusters and superclusters with large empty spaces in between that we refer to as voids. Now, as I said, cosmology is the study of the present, the past, and the future. So based on all these observations that we make, what cosmologists do is try to infer what happened in the past and what might happen in the future. And the tools that we use are, or the theory that we use is Einstein's theory of general relativity and the equations therein. And I'll say a little bit about general relativity. By the end of this lecture, you can go out and talk to people about general relativity. I'll promise you that, but very little. Cosmology or astronomy is a very ancient science. Since time immemorial, humans have been looking out at the night sky. Since they were not distracted by Netflix and other such distractions, they could actually, at the end of a long, hard day, look out at the night sky and, see this wondrous collection of stars in the sky, other objects that seem to be moving in the sky, like planets, etc., and ask questions like, what's governing the motion of some of these objects in the sky? Has the universe been like this forever? Is it going to be like this forever? How did it start? Did it start? How is it going to end, or will it not have an end? Now, this curiosity led to the birth of science and mathematics, in particularly astronomy, in all societies. This wasn't happening just in one part of the world, it was happening everywhere. And why is that? Of course, people will wonder wherever they are. First of all, our ancient societies, they were all agrarian. And astronomy was actually one of our first applied sciences. Because people used to look at the position of the stars and make calendars. For example, if a certain star was in a certain position in the sky, you would say that the monsoon will come in a month, it's time to plow the land and sow the seeds. Similarly, in Egypt, when a certain star was in a certain position in the sky, they knew the Nile was going to flood in so many weeks, and it's time to plow the land and prepare it, plant seeds, etc. So it was extremely important to study stars and the positions in the sky so that you could create a calendar. The other aspect of astronomy was it was used for navigation. People have been restless all along. So they don't stay put. They'll go across the Gobi Desert. They'll go across the Thar Desert. Why, don't ask me, but they go. Okay? They go from one part of the world to the other. They get onto ships and go across oceans. And how do they navigate? There's no Google Maps. There's no maps. All they have at that point, they may have created maps, is they use the stars for navigation. So because you go off a little bit, instead of landing in the northern part of Africa, you'll end up in some southern part of Africa, right? So it was important that these calculations were also fairly precise, so you knew where you were going. So for navigation purposes as well, people were studying astronomy. And I've just listed here a set of people who in India were actually working in astronomy, and actually a lot of mathematics gets developed along with it, because if you want to calculate the position of stars and planets, you need a lot of mathematics. So you have Aryabhatta in the 5th, 6th century, Varahamihira, Brahmagupta, Bhaskara, and then in the 14th to 17th century, you have a very famous Kerala School of Mathematics and Astronomy, where a number of people were working on trying to figure out positions of stars and planets in the sky, etc. But people were not working in isolation. There are books in Sanskrit, I'm not pronouncing it right, Romana Sahitika or something of that sort, which is actually a book of astronomy based on what people had learned from the Romans. And by the way, this is the Eastern Roman Empire, the Byzantine Empire, which was closer to us. So ideas of astronomy that the Romans had developed were used in India. Similarly, ideas that we had developed were used in the Arab world and were used in China. How did these ideas get across? Who were the people who were going? There were the people who were going from point A to point B had to know some astronomy. As I said, they were using the stars to navigate. So when they go from here to Iraq, to Mesopotamia, they will tell them about, okay, this is what we know about the stars. These are the stars we see in our part of the world. And they will tell them about stars that they see in their part of the world and the calculations that they have done. And that's how ideas went from one part of the world to the other. So that was up till the 17th century. A major development happens in the 17th century, and that is the invention of the telescope. And Galileo, who didn't discover that, or he didn't invent the telescope, but he used it extensively. In fact, he increased its magnification, etc. He now started making a lot more observations that were not available earlier. And based on his observations, for example, on something about the phases of Venus, etc., he concluded that a better model of the solar system was that the sun is at the center and the planets go around it. In the previous century, in the 16th century, Copernicus has already given us this idea. But it is Galileo with his observations who's pointing out that this model seems to work. Now, this was very disconcerting for people. People thought that the earth was at the center of everything. And I'll go on to say a little more about that. And here was this man coming along saying, no, the sun is at the center and all of us are going around it. But then people at least felt, okay, we've got the moon. The moon goes around us. And then Galileo goes around and he looks at Jupiter and comes back and says, you know what? Jupiter has 4 moons. Today we now know it has many more moons, but at least with his telescope he could see 4 moons. So people were very disconcerted by this. So this important scientific discovery had both philosophical and religious significance. If you look at all the religions of the earth, on this earth, gods, prophets, avatars, all came down on earth to bring about good in society. If the earth is not at the center of everything, then does it mean that these gods, prophets, and avatars were local, and in other planets or other parts of the universe, then another set of gods, etc.? So this shook people's religious beliefs. It required them to recalibrate their beliefs. And you can understand why that would have made people very uncomfortable. Galileo in particular faced a lot of persecution in his life for his scientific beliefs. Around the same time as Galileo, you have Kepler, who used the data from that had been collected by an astronomer called Tycho Brahe. And on the basis of that, he came up with something that some of you may have studied in high school, which is Kepler's laws of planetary motion. There are 3 laws. So these are empirical laws that he deduced by looking at the data that was available. Up to this point, there's no good understanding of the laws of physics that might be underlying all of these observations. And that's when Newton comes, also in the 17th century. And he gives us a law of gravitation. Supposedly an apple fell on his head, or maybe he fell on his head, God knows what happened. But he figured out some really fantastic law, which is the law of gravitation. Now, just as an aside, you remember in school they would always tell you it's the universal law of gravitation, and no one ever told you what was so special about this word universal there. Newton was looking at things falling on the earth. You drop this, it hits the ground. You throw a ball and it hits the ground. He was looking at gravitation between the ball and the earth. And then he made a magnificent leap of faith, in some sense, in the context of gravitation and said, this is a universal law that applies not just to objects falling on the earth, but to any two objects, may not even be planets, and also to the sun and the earth. He did not have an observation that implied that. All he had was things falling on the earth, but he made that law universal. That's why, these are signs of, of great insight that some of these leaders in particular disciplines have. And so he gave us the universal law of gravitation. Now, using Newton's law of gravitation, you can derive Kepler's laws. Kepler's laws are based on observations, while here was a law, an equation, etc., a theory that you could use to derive that. So that was a huge jump in our understanding. And then the next big major development happens in the early 20th century when Einstein gives us his theory of general relativity and applies it to our understanding of the universe. The theory of general relativity is a theory of gravity, just as Newton gave us a theory of gravity, but it goes beyond Newton's laws, Newton's theory of gravity, and works well in trying to understand the universe. So in just a couple of slides, let me tell you what is the theory of general relativity. As I said, it's a theory of gravity developed in the very early part of the 20th century by Einstein, almost single-handedly. And it changed the way we thought of gravity. So how do we think of, for example, a planet going around the sun? And we always say it's because of the gravitational force between them. You have the sun here, you have a planet, and there's a gravitational force pulling it towards the sun, and that's why if it had some initial velocity, it goes in a circular orbit around the sun. The centripetal force that is necessary for this circular motion is provided by a gravitational force of attraction between the sun and the earth. Einstein says there's no such thing as a gravitational force. It's not a force. There's a different picture for why this is happening. What he says is that you have the sun here. Its mass, or more precisely its energy density, modifies the space around it such that if you have another object moving here, in this modified space, it will go in a circle around it. So no force, but it's a modification of space. It's a very different picture, a very different way of looking at gravity. Now, this was a very radical idea. People they used to say in the early days that there were only about 3 people in the world who understood gravity, general relativity. I don't know if that was true, but today it's a standard thing. I mean, we even teach it to our undergraduates at Ahmedabad University as a full semester course. But in the early 1900s, this took everyone by surprise. Why? How did people think of space? Space is the arena in which physical phenomena occur. People knew about Coulomb's law. You take an electron, put another electron, and they repel each other. No one thought that these electrons were modifying the space in which this phenomenon was happening. But here comes Einstein and says, no, the presence of these electrons, of course they will repel each other, but it also modifies the space in which these electrons are sitting. His theory went on to say that space is also dynamic. The motion of these masses in space, as well as in some cases their presence, will cause space to also change in time. And I'll say more about that later. The theory of general relativity, though it took people by surprise, very quickly people started doing experiments to check whether its predictions were correct, and test after test showed that it was correct, and gave results better than Newtonian gravity. But we do teach Newtonian gravity in school, in college, etc. The law of gravitation, we teach our students how to solve problems using the law of gravitation, Newton's law of gravitation. So why is that? It turns out that you need to use the theory of general relativity particularly in three cases. One is if you want to do extremely accurate calculations for objects close to a very massive object. For example, the GPS system that we all use on our phones, on our smartphones, which tells you your position, fairly accurately. The way your position is calculated uses both special relativity and general relativity. The way it works is that you have a phone, there are satellites out in the sky, and you get signals from at least 4 satellites that come to your smartphone. It then makes a calculation about, based on the distance between your phone and these 4 satellites, it manages to figure out exactly what position you are on this Earth. But an understanding of how you do this calculation, the clock in your phone and the clock in the satellite has to be synchronized. But you would think that the clock is a clock. But general relativity tells you that clocks tick faster or slower depending on how far they are from a very massive object. So the clock in the satellite is ticking faster. And general relativity tells you how much faster it is going. If you don't take that into account in your calculations, as well as special relativity, within about 15 minutes, you will be about 100 meters off with respect to your position. And no Ola or Uber will ever be able to find you. Okay? So these general relativity has a very practical, when you want to do very accurate calculations, you have to invoke general relativity. If you want to understand the motion of objects moving close to the speed of light in the vicinity of a massive object, then you have to use general relativity. For example, Newtonian gravity tells you that light always goes in straight lines. General relativity will tell you that light will also bend. And finally, if you want to understand the universe, you need to invoke general relativity. In all other cases, general relativity reduces to Newtonian gravity. So your calculations of, if I throw a ball in the air and it falls on the ground, etc., all of those calculations work with Newtonian gravity. So let me get back to what is cosmology. Cosmology is the study of our universe today. How do we do it? We do it using ground-based telescopes and satellite-based instruments. Why both? Going out into space and putting your instruments out there means that you cut out atmospheric interference that happens when light is coming through the atmosphere. It gets distorted when it tries, until it reaches the ground. On the other hand, sending something up into space is extremely expensive, and in case there is some problem with that thing up there, then you have to send another mission to go fix it. You may have heard of the Hubble telescope. Well, the Hubble telescope went up there, and the mirror was not well polished. And they had to send a whole bunch of other people up there, very, very expensive, to go and, someone sat there and, did something to the mirror, polished it to make it right. Okay? Because before that, the images were coming blurred. These are reflecting telescopes, light comes, bounces off a mirror, and then gets collected at a detector. If this is not smooth enough, then you are going to have problems. So that's the disadvantage of satellite-based instruments. Having made all these observations, we then use the laws of general relativity, the theory of general relativity, more precisely Einstein's equation, which is the key element of the theory of general relativity, to make predictions about what might happen. What might happen in the future. That's a very small dot there, but anyway. What might happen in the future, or actually, I have a pointer in there, if you can just get a thicker pointer. Yeah. What might happen in the future and what we know in the past. Now, this is not just all theory. I mean, I'm a theoretical physicist, so I can keep, speculating and doing things. But my astronomer friends will go out and make observations and come back and say, your theory works or your theory doesn't work. So in a sense, this is just a slide to tell you how we play this game. Is it there? Is there a pointer in there? Maybe I forgot it. Okay, the gravity in this room is so strong it's bending the light. Neither pointer is going to work. Okay. You know, when you're studying in 11th and 12th, and I know you were all studying in 11th and 12th, you all except. Okay. You study Newton's laws of motion, right? So if I take a piece of chalk and throw it at you, if you know the initial position and the initial velocity, I can predict where it's going to go. Similarly, if someone throws a piece of chalk at me, because I'm a professor of physics, if I know the position and the velocity, I can know exactly which one of you threw that piece of chalk at me. So do not try that. Okay? It's the same principle here. We make our observations today, then we use Einstein's theory of general relativity or Einstein's equation to predict what might happen in the future. Or based on our observations today, we can go back in time and say what might have happened in the past. So let's then try to understand what do we know about the present, the structure of the universe, the dynamics, the composition, and then based on that I'll tell you what we know about the past and the future. There's a question mark about the future because there are certain things that we do not understand about the future. Okay, so what do we know about the present? If you look out at the night sky, you will see lots of stars. You'll see them with planets. You'll see stars grouped into galaxies like our Milky Way. You have groups of galaxies which are called clusters. Clusters are grouped into superclusters with empty space in between them, which are called voids. Now, our sun is not special. There are billions of stars like our sun in our galaxy. And like our sun, there are planets going around many other stars. We have so far discovered about 6,000 exoplanets. A planet going around a star other than the sun is referred to as an exoplanet. So we've got about 6,000 of them so far. Planets are very hard to discover. You know, the star itself is very far away. It's like a dot out there. And now you have this even tinier dot going around it. So very hard to discover. There are two ways in which this is done. One is, if this is a star and you have a planet going around it, you can't see the planet, but you can measure the light coming from the star. And you will see that there's a periodic dip in the amplitude, in the intensity of light coming from the star. And on the basis of that, from the period and the amount of the dip, you can conclude that there is an object of a certain mass at a certain distance, possibly going around the star. So that's how you discover many planets. Another way is that, you know, when we look at our solar system, we think here's the sun and we have all the planets going around it. That's not quite the right picture. The sun and the planets are actually moving around the center of mass of this entire system. So if you just think of one planet and the sun, the center of mass of this system is not at the center of the sun, but it is slightly displaced from the center of the sun, which means the sun is also doing this. It's moving around a little bit. Now, you've heard of the Doppler effect, at least in the context of sound. If an ambulance is coming towards you, its frequency goes up. When it's going away from you, so there's a shift in the frequency of sound when there's a relative velocity between the source and the observer. The same thing happens with light waves. So if you have this star that's over here and the planet is going around, you can't see the planet, but this thing is shifting like this. Now the light coming from this star, we know what will be the frequencies because there'll be some atomic transitions associated with hydrogen or helium or sodium or whatever are the elements in a star. You will notice that the frequency of that light is shifting. And on the basis of that, you can discover that there is a planet around there. Very close by, Physical Research Laboratory, where I was a faculty member for 20 years, we have a team that is actually working on discovering exoplanets using these ideas, this technology. We use the Mount Abu Observatory. PRL has an observatory at Mount Abu, and that's where these experiments are done. And in 2019, Mayer and Kellos got the Nobel Prize for the discovery of an exoplanet around a solar-type star. By the way, this wasn't the first exoplanet to be discovered. There was one discovered around a pulsar, which is a small magnetized neutron star. But this was the first around a solar-type star. And where it was well confirmed that, yes, this is an exoplanet. Now, why does someone get a Nobel Prize for discovering a rock going around some star somewhere? Okay. Sorry, didn't mean to belittle you guys, but it was a very tough experiment to do. But what's the relevance of this? Okay. The point is that the scientific community has already started looking for another planet for the human species. We know that this planet will not survive forever. One is, so the solar system has a finite lifetime, long beyond our lifetime. It's about another billion years at least. But this planet cannot survive forever. And hopefully, due to climate change and wars, I hope we don't destroy our planet even before other reasons destroy it. But anyway, the search for another planet is on already. Now, what's the kind of planet you're looking for? Any old planet around a star won't work. If the planet has a mass similar to that of the Earth, then the gravity of that planet will be similar to that on Earth, which will make it easy for us to walk on it. If it is something like the moon, if you've seen pictures of astronauts, they're always jumping on it because the gravity there is so weak because it's a smaller, massive object. If you were on a planet that had the mass of something like a Jupiter, then you would be crawling on it. You wouldn't be able to move. Okay? So that's one reason why you want something about the size of the Earth. The second is that the atmosphere that surrounds a planet, and we are sort of used to oxygen and nitrogen in a certain mix, is a function of what is the mass of that planet, because that traps gases of certain molecular weight. So that's why the moon is very light. The moon has very little mass, so it doesn't really capture very much. There's no atmosphere there. So you want something that's about the size of the Earth and the mass of the Earth, so it captures an atmosphere which is about the size, which is amenable to human habitation. The other important factor is that that planet must be at a distance from the star that is similar to the Earth from the sun, because then the temperature on that planet will be habitable, will make life habitable there. It will also determine what is the atmosphere on that planet. So it's called the Goldilocks zone. We're looking for a planet which is just right, if you know the Goldilocks story, for humans. That is why the search for exoplanets has been going on. I think in 95 is when the first one was discovered. In now about 30 years, we have about 6,000 discovered. Of course, the technology to reach another planet we don't have yet. That'll take a long time. But you guys can start designing houses for the planets, okay? Stars, okay, are grouped into galaxies. Galaxies come in different sizes and shapes. You have elliptical, spiral, irregular, spherical, etc. This is a galaxy that's often referred to as a twin of the Milky Way galaxy. It's a spiral galaxy. There's a central bulge, and there is gas and stars in spirals around it. If you went out of the Milky Way, you would be able to see something like this. Of course, we're in the heart of it. If this were the Milky Way, where would we be? We, special humans. We are carbon life forms living on a rock, going around a star somewhere at the edge of this galaxy, of our galaxy. So we are not that special. On the other hand, it's impressive that these carbon life forms living on a rock can actually use their imagination and their intellect and say something about the whole universe. And another thing, at the center of most galaxies is sitting a supermassive black hole. So at the center of our galaxy is a black hole which has the size of about 4 million, has a mass of 4 million suns located in an extremely small area. But all our galaxies have it, and Penrose and Genzel and Guess got the Nobel Prize for both theoretical underpinnings of black holes as well as the actual observation of the black hole at the center of our galaxy. Here's another picture of the Andromeda galaxy, another galaxy. It is not the nearest galaxy to us, it's the nearest large galaxy to us. It's part of our locally gravitationally bound system. And please do stare at it, because in 4 billion years it's going to crash into the Milky Way. Galaxies are grouped into what we call clusters, and each of these yellow things is a galaxy, so they're all grouped together in what we call a cluster. And these clusters then group themselves. This is not a computer-generated picture, by the way. This is based on observations. So you will see galaxies and clusters of galaxies coming together, forming filaments, and a lot of empty spaces that we refer to as voids. So that is the structure of the universe today. That's what we know about the universe today. Let's now talk about the dynamics of the universe. Is the universe static? Is the picture I'm showing you right now the picture that you expect to see billions of years from now? When Einstein first applied his theory of general relativity to the universe, he presumed that it was static, that it would not change in time. But there were a bunch of observations that were coming in around that time. One was by Westo-Slipher, who said that distant galaxies all seem to be moving away from us. What you would expect is that some of them should be coming towards you, some of them should be going away from you. But when you looked at distant galaxies, they all seem to be moving away from us. And how did he discover that? By looking at the red shift, that is the downward shift in the frequency of the light coming towards us, which meant that that galaxy was moving away from us. But then comes Hubble and Humason, who point out a bit later than him, that the speed with which galaxies are moving away from us is proportional to their distance from us. Now, this had immensely huge implications. This is known as Hubble's law, that the recession velocity, the velocity with which things move away from you, is proportional to the distance they are from you. And the proportionality constant is called Hubble's constant. And Lemaitre in 1927 had also given a theoretical model as to why this might happen. So let's see what's the implication of this. Supposing we are over here in this galaxy, and you have other galaxies at a distance of 10 light years, 20 light years, 10 light years, 20, 30 light years away. Now the observation is they're all moving away from us. And let's say they're moving away from us at a speed proportional to their distance from us. So I could say that this is going away, pointers, yeah, that's moving away from, this one is moving away at, let's say 10 kilometers per hour. It'll be, I'm just making up numbers. Astronomical numbers would be very different. So 10 kilometers per hour, this will be going at 20. This would be going at 10 kilometers per hour. This is 20 kilometers per hour in that direction. This is 30 kilometers per hour in that direction. Fine. Now you move to another galaxy. Move to this galaxy. And there's an astronomer there, and she makes her measurements. And what will she say? Well, you know the relative velocity between this galaxy and this. So she would say that this galaxy, which is where our galaxy is moving away from her at 10 kilometers per hour. This one is moving away at 20 kilometers per hour. This one is moving away at 30 kilometers per hour. I'm just adding 10 to each of these because the relative velocity between us and her galaxy is 10. And similarly, this is moving at 10 in this direction. This is moving at 20 kilometers per hour in this direction. So what does this mean? This means that wherever you are in the universe, whichever galaxy you're in, it seems like all the galaxies are moving away from you. It's not a Milky Way or Earth-centric phenomenon. It's happening everywhere. And this is the statement that the universe is expanding. Wherever you're in the universe, distant objects seem to be moving away from you. And that's called the expansion of the universe, which means the universe is not static. And Einstein admitted that he had made an error in his presumption, the assumption that the universe would be static. A question that often gets asked is that, hey, if everything's moving apart, then why does the solar system remain in some kind of a compact form? Why do you and I not move away from each other? Remember, I kept saying distant galaxies. Distant galaxies means they're not part of a gravitationally bound system. If you're part of a gravitationally bound system, your local gravity is going to be stronger than the average gravity of the universe that is taking things apart. And that's why the solar system maintains its shape and size, while distant galaxies are moving away from each other. One thing I want to point out is that the reason things are moving away from us is not because of any intrinsic velocity of these objects. It's not like this galaxy got a kick, something hit it and it's moving away, another galaxy got another hit and it's moving that way. If that were the case, then half of them would be coming towards us and half of them would be moving away from us. So what is happening here, that everything that's far off from us is moving away from us? How do you explain this expansion? And the way to think of it is that the space is expanding. You have space in which galaxies are embedded. Einstein's theory of general relativity tells you that space is dynamic. Space gets influenced by the matter in it. And the understanding of the expansion of the universe is not that these galaxies had some velocity of their own, but the space in which they're embedded is dynamic and that is expanding. So the space between galaxies is increasing and carrying the galaxies along with it, and that is why you're seeing an expansion. Now, can we understand this expansion? Can we say something about the speed of expansion, etc.? You can do it through observations, of course, but you must also have an underlying theory that explains it, and that's where the theory of general relativity plays a role. What it tells you is that the rate of expansion depends on the average mass density in the universe, or the square root of it, but it depends on what's the mass density or energy density in the universe. It also depends on whether the universe is made up of relativistic particles or non-relativistic particles, or, as we discovered very recently, something else. And we'll talk about that. So we've looked at the structure of the universe at present. We looked at whether it is static or dynamic. Well, it is dynamic. And I've told you that to understand the dynamics of the universe, you need to understand what makes up this universe. So that's the composition of the universe, which is what we'll talk about now. If you take a receiver, a detector of electromagnetic radiation, and point it in any direction in the sky, away from stars and galaxies, what you will pick up is radiation, which is also, we refer to it as photons, if you think of it as particles, coming at you, reflecting a bath of photons at a temperature of 2.7 degrees Kelvin. Very, very low. That's like minus 270 degrees centigrade. So it's like there's a thermal bath of photons out there, and photons are relativistic, out there in the universe. We refer to that as the cosmic microwave background radiation, and this was discovered in the 1960s. There's also another set of particles that are very light. They have a mass much smaller than that of an electron, and they're referred to as neutrinos. They're produced in nuclear reactions. So, for example, in the sun, you are producing neutrinos all the time. In nuclear reactors, we're producing neutrinos all the time. The ones from the sun just go right through us every second. They don't interact with anything. They just go right through your body. And that's why now there is throughout the universe, there's a background of these neutrinos that are left over from the very early times of the universe. It's called the cosmic neutrino background. And so far, no one has detected it because it's so difficult to detect neutrinos. We have detected neutrinos coming from the sun, neutrinos that come out of nuclear reactors, but not the cosmic neutrino background. Okay, so that's the relativistic stuff in the universe. Then, I mean, what's our most common feature of the universe? You look out, you see stars, you see galaxies, you see a lot of light coming from there. So what's the source of this light? So if you look at a galaxy, this is a picture of something called the pinwheel galaxy. If you look at it, you will see that there's a lot of light coming from it, particularly from the center. And what's in these galaxies? There's stars and gas. the gas in the stars are made up of hydrogen and helium predominantly. Hydrogen in helium is made up of protons, neutrons, and electrons. These have electromagnetic interactions which produce light. And therefore, we can say that galaxies have a lot of luminous matter. But when people were making observations of the speed with which stars at the edge of a galaxy are going around the center of a galaxy, and you would have studied in school that the centripetal force is equal to the gravity. If something is going in a circle, you need a force acting towards the center. That's what we refer to as the centripetal force. In this case, most of the mass of the galaxy is in the bulge here. That's where most of the light is coming from. So you can say that the mass of this galaxy is more or less fixed, and these stars are going around. And if you just equated the centripetal force mv squared over r, where m is the mass of the star, to the gravitational force gmm upon r squared, where capital M is the mass that is sitting pretty much in the bulge of this galaxy. That's where most of the galactic mass is. You will get that the velocity should be going like 1 by square root r. What that means is that if you look at a star here, then a star here, and a star here, the velocity with which it is going around the center of the galaxy should be decreasing with distance. And yet, in galaxy after galaxy, what we're seeing is it is not falling as is expected, but is doing something like this. Here it seems to be going up, but in most galaxies it's basically flat over here. That is, beyond a certain distance, the speed with which it's going around the center is not going down, which it should if all the mass was sitting in that bulge. It's staying flat. The only way you can explain this is that if you go back to this equation, and this capital M, which is the mass of the galaxy, you make it equal to a times r, then you'll get velocity is constant. Now, if you say the mass is a times r, that means as the distance keeps increasing, there is more matter there. But we're not seeing that matter, because the matter that we're seeing all seems to be in the bulge. So there is more matter in the galaxy that we're not seeing. And that's referred to as dark matter. Now, you might think that this is a small effect, but it turns out 90% of the mass of a galaxy is due to dark matter, and only 10% is due to luminous matter. So it's a huge effect in galaxies. Now, you can see an object if it emits light, like the sun, or if it scatters light, like the moon. The stuff that's making up the dark matter neither emits light nor scatters light. And that's why we're unable to see it. It doesn't interact very much, and that's why we've not been able to detect it so far. This is not a new discovery. We have known about dark matter since the 1930s. It was in the 1930s that people realized that galaxies and clusters have dark matter. Until today, no one knows what makes up the dark matter. We know its effects, but we don't know what's the name of the particle that makes it up. There's dark matter in this room. There's dark matter between you and me. When I wave my hand like this, it's going through the dark matter. But I can't see it, and it doesn't interact with my hand, and therefore it just goes through my hand. It's all over in the universe. Until date, we don't know what it is. You may have heard of the Large Hadron Collider at CERN, which discovered the Higgs boson several years ago. What is it? It's a huge accelerator where you take protons and you accelerate them in a loop like this, another set of protons and accelerate them like this, and bam, you crash them into each other. When they crash, the proton breaks up and you can see what's inside, which are quarks. But also, you can create new particles because the kinetic energy of the protons that are colliding gets converted into new particles, like the Higgs boson. That $8 billion experiment had only two jobs. It was supposed to discover the Higgs boson. It was supposed to discover the dark matter particle. For $4 billion, they've got paisa vasool. But for the remaining $4 billion, we're still waiting for the Large Hadron Collider, hopefully, to find the dark matter particle. So far, we don't know what it is. Okay, if that wasn't embarrassing enough, that we don't know what 90% of our galaxy is, somewhere in 97, 98, people were looking at the light coming from supernovae and trying to measure how fast the universe is expanding, and realized something. That for the most part of the history of the universe, so the universe is about 14 billion years old, 13.8 billion years after the Big Bang. For the first 9 billion years, the universe was expanding and slowing down. So distant objects were moving away from each other, but the speed with which they were moving away was decreasing. What they discovered is that in the last 5 billion years, it's speeding up. So we are now in what is referred to as an accelerating universe. We have an understanding of what might have caused what would have caused the deceleration of the universe, but we do not know what is causing the acceleration of the universe. You could go into Einstein's theory of general relativity and make some modifications, introduce something called a cosmological constant, and that will explain why the universe is accelerating. On the other hand, you could introduce some new field that pervades the universe that has a property that it makes the universe not just expand, but it makes the universe accelerate while it's expanding. We refer to that as the quintessence field. Fields are known to us. You've studied magnetic fields in school. We know in galaxies, for example, there are magnetic fields across the length or breadth of the galaxy. So maybe there is some other field out there that's across the universe. We refer to it as the quintessence field, but as of today, no one knows whether it's a modification of Einstein's theory of general relativity, it's this introduction of a quintessence field, what is the quintessence field, etc. Whatever may be the source of this acceleration, we refer to it as dark energy. In some sense, the dark is about our ignorance. We really don't know what is causing the universe to accelerate. Okay, so what I've told you is that the universe is made up of relativistic particles, photons and neutrinos, luminous stuff, protons, neutrons, and electrons, dark matter, dark energy. I also said that the dynamics of the universe depends on the composition of the universe, whether it's made up of relativistic stuff or non-relativistic stuff. So if you try to estimate in today's universe which is dominating the energy density of the universe, what's there more in the universe, it turns out the photons and neutrinos are negligible. The protons, neutrons that make up you and me make up only 5% of the universe. Dark matter makes up about 27% of the universe. And dark energy makes up about 68% of the universe. It's very comforting. We don't know what makes up 95% of the universe. We only understand 5% of the universe. Nevertheless, because we know a lot of things about the properties of dark matter and some things about the properties of dark energy, we are still able to make a lot of comments about what the past was like and what the future is about. And that's what the last part of this lecture will be about. So what do we know about the past and the future? So the question we want to ask is, was the past always like the present? Is it going to continue like the present? And we know that the universe today is expanding. And we have our equations. So what we know today is that all distant galaxies are moving away from each other. If you take, so now let me try to go back in time. Let me take a finite region of space. There's a lot of matter out there. Stars, galaxies, whatever it is. Now I go back in time. The same matter is in a smaller and smaller volume, which means it's getting denser and denser and denser. As you go back in time, so we are at about 13.8 billion years. As you go back in time, what we know is that you won't have any molecules. They'll break up. Because as you go back in time, things are denser, things are hotter, things are more energetic, so things break up. So molecules will break up. You go further back in time, atoms will break up. You go further back in time, nuclei will break up. Go further back in time, protons and neutrons that make up a nucleus will break up into quarks. You keep going back in time. If you go back to the earliest that we can sort of predict using our equations, you will find that that universe at that point is extremely dense. The particles in there have very high energy, and they're all moving apart very fast. This initial state with very high density and extremely fast expansion of the universe is what we refer to as the Big Bang. The Big Bang is the initial state of the universe when everything is moving out extremely, extremely fast. And very dense time, very high energies of particles. Now, there's a misconception about the Big Bang that all the matter was located at a point and it all exploded. That's not what happened. The matter didn't explode. It was the space that exploded, taking the matter along with it. And the term Big Bang actually confuses people, partly because the person who coined it was an opponent of the model. The way to think about it is actually, if you take any finite region in space, go back in time, that would become an extremely dense region, and it's moving apart very fast right now. So that was the Big Bang. What happened after that? We actually have a fairly good reconstruction of the history of the universe. In the first 1 second, which is the area, the period that my research is about, you had a hot primordial plasma. It had all the particles in their elementary form. So you have electrons and quarks and gluons and photons and neutrinos, dark matter particles, etc. As the universe slightly cools, the quarks come together, form protons and neutrons. Around 1 second, from 1 second to 3 minutes, is when the first nuclei start forming. No atoms at this point. And you only form the light nuclei. Hydrogen nucleus is just a proton, not much to form there. You form the deuterium nucleus, which is neutron and proton. You form tritium, you form helium-3, you form helium-4. You get lithium, and then it stops. This is what we refer to as primordial nucleosynthesis. You only create the light elements at that point. The heavier elements that make up you and me, carbon, nitrogen, potassium, etc., those were created in stars much later, in the nuclear fusion that happens in the core of stars, as well as when supernova explosions happen, when a star explodes. About 400,000 years is when the temperature in the universe has cooled down enough that an electron and a proton can find each other and form a hydrogen atom. Even prior to that, they were forming, but what would happen is some very energetic photon would come and break it up. Kabab mein haddi. But now what happens is that the temperature is low enough, the photons don't have enough energy to break up this pair. And now you're producing the first atoms in the universe. 300 million years is when the first stars form. 1 billion years is when the first galaxies form. 9 billion years is when, as I told you, the universe starts accelerating. Incidentally, the solar system was also formed at that point. These are not correlated. And 14 billion years is where we are today. You notice some star asterisks over here. That's because the James Webb Telescope is now telling us that, excuse me, is there a question? The James Webb Telescope is now telling us that our understanding of when galaxies formed may be a bit flawed. They don't happen at 1 billion years. They may be happening even earlier at 300 million years after the Big Bang, which may cause us to change our understanding of how galaxies actually form. And even the earliest stars may be earlier than 300 million years. Now, this is not just a story. This is based on theory and confirmed by observations, or observations are first made and then confirmed by the underlying theory, by theorists. And Professor Peebles got the Nobel Prize in 2019 for contributing in many ways to the understanding of the early part of the universe, or the past of the universe. So the future. We're always interested in the future. Actually, there are huge question marks here. We don't know what's going to happen. And the reason is, we don't know what makes up the dark energy, and we don't know enough properties of the dark energy to make concrete statements about what's going to happen in the future. When it comes to dark matter, we don't know what makes it up. But we have enough information about dark matter that you can make statements about what happened in the past. But for the future, we don't know. Will the universe keep expanding? Don't know. It may keep expanding forever. Or there are also models of cyclic universes. The universe expands, things move apart, then they come back together. Then once again they move apart, and then they come back together. It's called a cyclic universe or an ekpyrotic universe. It may continue to accelerate as it is doing today, or it may not. So there are many different expanding scenarios. Let me just give you a glimpse as to two possibilities. There are many more. Let's just presume that the universe is going to stay expanding. It's not going into this cyclic mode. One model states that all distant galaxies will move away, but the galaxies will retain their character. And over a period of time, the stars in them will keep shining and then run out of fuel, and the galaxy will become dark, and the universe will gradually become dark because there's nothing burning, nothing shining, no stars are shining in it. There are other models, and that would take only about 100 trillion years, so you don't need to worry too much. The other is that the galaxies move apart. Within the galaxies, now the stars move apart, and then the stars start breaking up too. And ultimately your universe is filled up with a dilute cold gas. And that could take about 50 billion years. Not sure which one of these pictures or one of the other many pictures that exist is right, but we don't have to worry. Solar system is going in about 7.5 billion years, long before this. Okay. What's going to happen is, first the sun is going to enter something known as the red giant phase. So the sun, if we talk of global warming on this planet, the sun is also warming up for other reasons. And slowly it will get hotter and hotter and hotter. In about 1 billion years, the temperature on the sun will be high enough that all water, Coca-Cola, alcohol, wo to Gujarat mein nahi hai, but anyway, at least water, Coca-Cola, etc. is going to evaporate. But the earth will still be there. But in about 7.5 billion years, the sun is going to expand in size. It's called a red giant at that point. The size of the sun will be greater than the orbit of the earth. So either the earth gets subsumed within the sun, or we get kicked out even further. In either case, I don't think human species is going to be in any shape or form to be able to last through this the destruction of the solar system. So let me end by summarizing what we know today and what are the important questions in cosmology. So what we know is that we live in an expanding universe. The initial condition was you have a very dense, energetic, fast expanding state, which we call the Big Bang. The universe today is made up of stars and galaxies, clusters and voids, which we call the structure of the universe. There's also a lot of dark matter in these structures. And finally, we have an accelerated expansion in the universe today. But we are unsure about the future because we don't fully understand, or we don't understand enough about what's driving the expansion of the universe. What are the outstanding questions? Homework problem for all of you, due by tomorrow. One, why the Big Bang? I said this Big Bang happened. What actually happened there? What caused it? What came, if you can ask, before, or what led to it? Answer is we don't know. We have no clue. Or we have theories, but we don't really have a good understanding. The reason is that at those high densities and those high energies, you need a quantum theory of gravity. Einstein's theory of gravity is a classical theory of gravity. But at those high energies, you need to bring in quantum effects, and we don't have a good quantum theory of gravity. Some of you may have heard of something called string theory or loop quantum gravity. Those are all quantum theories of gravity, but as of now, they're not well formulated enough for us to really apply them well. The second is, what is the nature of dark matter? As I said, the Large Hadron Collider is looking. There are other detectors that are looking for dark matter. but as of now, we don't know what it is. And finally, we can't make a definitive prediction of the future as some parameters are not measured yet. And so observations are going on now to understand and appreciate what might be the nature of dark energy. So maybe in a couple of decades, which is the sort of time scale on which you make important discoveries, at least a decade or more, we might have a better understanding of what is dark energy, what is driving the expansion of the universe, the accelerated expansion of the universe today, and then we'll be able to make a better prediction of what's going to happen in the future. So let me now finally just leave you, in case you're interested in these kinds of ideas, just leave you with some references that you could look at. One is a book that I read during my PhD time, so it tells you it's a bit old. The First 3 Minutes by Steve Weinberg, a very famous physicist who's unfortunately no more. It is an old book, so it doesn't even talk about dark energy. It wasn't discovered in his time, but has a very good explanation of the universe. There's an excellent series of books by G. Venkataraman, who was an Indian physicist at the Indira Gandhi Center for Atomic Research in Tamil Nadu. And he wrote a series of books. One of them is called The Big and the Small, which has a lot of stuff on cosmology. And finally, they're online. There are some resources. You can't read it, but they're out there. And that's my email ID there. You're always welcome to reach out to me in case you figured out any of the answers that I left behind. Please do reach out to me. I'd be more than happy to discuss them with you. Thank you. Thank you very much. So is there a question answer session? Or?
Thank you so much, sir, for such an insightful lecture. We are open to question and answers right now, if anyone has any.
There's one in the back there. Yeah, it's working. No, it's working. The mic is working.
Hello.
Yeah.
Okay. So you had mentioned about how the first nuclei were formed, and then you had said that it was helium and lithium. So my question was, why wasn't hydrogen the first nuclei formed? Because it's just one proton.
In fact, I mentioned it. I said hydrogen is formed, but there's nothing to form there because it's just protons, and protons already existed. So you didn't need to do any further fusion to create the hydrogen nucleus. Okay. But you do form deuterium, which is proton plus neutron, which is an isotope. Yes.
Thank you.
I actually wanted to know more about the work you're doing right now.
So the work I do is on something called the matter-antimatter asymmetry of the universe. We believe that the very early universe had equal amounts of both matter and antimatter. So antimatter is nothing very exciting in some sense. It's, if you have an electron, you have something called an anti-electron, which has all the properties of an electron, same mass, spin, etc., but it has the opposite charge. Now, the anti-electron is also called the positron. It was discovered in the 1930s, etc. So for all particles, you have an antiparticle usually. So we believe the early universe was made up had both particles and antiparticles. But if you look around the universe today, you will see that it's made up only of particles. So our planets are made up of particles. You and I are made up of matter and not antimatter. Otherwise, if we shook hands, we would annihilate each other. Okay? So the question that is asked is, where did all the antimatter go? If you started off with equal amounts of matter and antimatter, why is today the universe made up only of matter? Why are galaxies made up only of matter? Excuse me. Our understanding is that you started off with equal amounts of matter and antimatter. Let's say you had 100 protons and 100 antiprotons. Due to some imbalance in the universe, very early universe, this became 101 protons and 99 antiprotons. Then these 99 antiprotons annihilated 99 protons, And all that we see in the universe today, you, me, I, stars and galaxies, are made up of the remnant of that annihilation that happened in the early universe. My research is about understanding what caused that imbalance. And there are many models, many ideas that we work on.
I also wanted to ask about the recent discovery NASA, the Perseverance rover made on Mars,
Sorry?
about the biosignatures Perseverance rover found on Mars. Do you know anything about that?
So I don't work in the solar system, but the question is about some biosignatures. So I think some molecules were discovered which they believe can come only from some kind of a organic reaction involving life forms. And they're speculating that that may be due to some form of life that was there. So, you know, I keep saying there's nothing special about the Earth. Okay, and sorry to say there's nothing special about any of us. Okay, so out there in the universe, it's likely that some other kind of life form does exist, but it may not be like us. It may not be carbon-based life forms. It may not have a head and two hands, etc. It may be something extremely different, but it's not unlikely that somewhere out there. Now, on Mars or within our solar system, the conditions have to be right so that the kind of life forms that we're familiar with should exist. In fact, there's a joke that the surest sign that there is intelligent life out there is the fact that they have not made contact with us. I think it's a Calvin and Hobbes joke. Yeah? Yeah?
Hello.
Yeah.
So my question was about, are voids also made up of dark matter?
Likely not.
Then what are they made of?
So they could just be space, empty space. There could be some dark matter there.
Okay.
There will be dark energy there. There can be some dark matter there because the picture I showed you is about luminous matter, galaxies, clusters, etc. There could be some diffuse dark matter there, but where the galaxies are is actually where the dark matter is also concentrated. In fact, it's the other way around. Where the dark matter is concentrated, the galaxies are forming.
And what is the difference between dark matter and dark energy? Do we know?
We do know the differences in some of their properties. For example, dark matter is likely to be made up of some particle and has a certain form of its pressure, while the dark energy is most likely not a particle, but maybe something like a field, and something known as the pressure associated with that field is negative, unlike that for dark matter where it is positive. So they're very different in their form.
And one more thing, light, like Newton said light moves in a straight line, but Einstein says that light bends. They're paradoxical, but they're true. How?
No, one is wrong, the other is right.
Okay.
Newton is wrong, Einstein is right.
Okay.
It was seen in 1919 that light bends around the sun. During a solar eclipse, when the sun was hidden, so otherwise if you try to look at the sun, I mean, you'll go blind, right? So you have an eclipse and the sun was hidden, and there was a star somewhere behind it, which you normally should not have seen. Actually, technically you would have seen it. It was a bit to the side, but let's just say you would not have seen it. But now, during the eclipse, the light coming from it, instead of, if it was coming straight, it would have hit the sun and not reached us. It bent and came around and saw us. It was bending even when there's no eclipse, but when there's no eclipse, the light from the sun overwhelms this light so you don't see it. So during that eclipse, they saw stars that if light goes in a straight line, you should not have seen. And I think there was a question somewhere here too. Yeah. Yeah.
So is there maybe a connection between the expansion of the universe and the passage of time? Like, for example, if it started contracting and everything started breaking apart again, would that be called reversing time or something?
No, it's just going forward in time.
Just going forward.
It's just going
Okay,
forward.
sure.
You mentioned that space exploded when the Big Bang happened and not matter. Could you help me understand that more in detail?
So it's a little tough to wrap your head around. So let me, what I'm saying is this, that something today you have a finite region of space, you go back in time, it's a very small region of space. It's very dense. There's a lot of matter there, okay? And then at that instant, the space is moving apart, carrying with it the particles on it. It's difficult to appreciate because you don't think of space as changing in time. But Einstein's theory of general relativity, and many experiments have shown it to be correct, that space, there's no conservation of space concept, and space can also change. So if you and I were distant galaxies, we are in space, and the space expands. It's like the surface of a balloon. If you put two dots on it, and you blow up the balloon, you notice that the points are moving apart. They are not moving because of any velocity of themselves. It's just that that surface on which they exist is expanding or stretching.
Also, one more question. When the Big Bang happened, there was like a rapid like it was moving really fast, right? It was expanding really fast, and it has been it decelerated after. It's accelerating again. So, do you think that we'll have to reach those Big Bang speeds again to like decelerate again?
No,
Like,
so yeah, I mean, in a sense, initially the universe was expanding after the Big Bang, but slowing down, except for a very brief period in between called inflation at 10 to the minus 32 seconds. But anyway, it was expanding but slowing down. Then at 9 billion years, it's continuing to expand and speeding up. Now, could we get back to a Big Bang scenario? Possibly. In what we call the cyclic universe, the universe stops expanding, and now things start coming together. And it will come closer, and then once again start expanding. In those scenarios, the Big Bang that we see is actually coming after a contraction of the universe and then an expansion. So we are in an expanding phase of a cyclic universe in which you expand and contract, expand and contract. Is that model correct? No one knows.
so there are chances we are not the first universe and the first cycle in this universe.
Yes.
Thank you.
Hello.
Yeah, go ahead.
So when they mention the birth and end of the universe, there is a term that is commonly mentioned, the space-time fabric. Could you give an outline of what that is?
Okay. It's not so much in the context of birth and death of a universe. Even you have space, you have the 3 dimensions of space, and you have time. Yeah? Things evolve in time in this space. So body moves in space. When we say it moves, that means at different times it's at different positions. The earlier laws of physics, you treated space in a certain way, you treated time as separate. So you would say the position in time. So x was a function of time. When Einstein formulated his theory of special relativity, he said that, and you know, whether you were in a car or you were in an accelerating bus or you were in a plane, your positions would change, but your notion of time did not change depending on where you were, on your frame of reference. What Einstein said is that that's not quite the way it is. In his theory of special relativity, space and time are intertwined, and when you go from one frame of reference to another, your notion of time itself can change. And the only way to understand that is by saying that space and time are basically a set of 4 coordinates, not 3 of space and 1 of time. And that's why we just use the term space-time. Fabric, don't worry about that.
Thank you, sir.
Sir, so physicists all around the world have been searching for the unified field theory. So do you think that quantum loop gravity or even string theory will yield any results? Because as of right now, people all around the world are very caught up in their own stagnating ideas. And do you think that if somehow we're able to observe the universe on a Planck length, then and only then will the fundamental force of the universe unify?
So there are many ideas of, string theory, loop quantum gravity. The energies to which you need to go to actually make those measurements, you talk to the Planck length, let me talk of the Planck energy, which is an energy scale at which you need to go to actually do experiments where these things can get measured directly. The energy scale at which we currently work is about 1,000 in some units. So that's 10 to the 3. The energy scale we need to reach to actually do experiments at at the level at which string theory and loop quantum gravity become fully applicable, is 10 to the 19, which is 16 orders of magnitude. So there's not going to be any technology in the near future that is going to be able to, probe those energy scales. However, just as Einstein's theory of special relativity, which is valid at speeds close to the speed of light, you can look at, and then you have Newton's theory of motion, laws of motion. You do your calculations using Newton's laws of motion. You don't have to go close to really very close to the speed of light to start seeing some of the effects as first order or second order effects in your motion. So if you can come up with more and more sensitive instruments and design clever experiments, even though you don't go to the highest energy scale that you need, even at lower energy scales, you will see deviations from what we call the standard model of particle physics. And those deviations will give us an indication as to the larger theory that it operates at a much higher energy scale. So people have been trying to be clever about thinking of experiments at the energy scales that we are at today, or a little more than that, and to see what might be the effects. These are what we call perturbations in our standard ideas. What will be the deviations from what we expect from our current ideas, which may give you an indication that the current theory is wrong, you need that theory, and these are the elements of that theory. So far, we have not been too successful, but give us more funding, we'll do it.
Hello.
Yeah.
Sir. Here. Sir,
Which
thank you
part
for...
of space-time are you in?
Here, sir.
Okay, yeah.
Thank you for this seminar. And my question is that you said that a quantum theory is required to understand. So who is working right now on quantum theory? And is there any other theory to help us to understand this universe?
So the quantum theory of gravity, quantum mechanics is now well established. Came in the 1930s, very well established. Quantum field theory, which is for relativistic particles, came in the 1950s, well established. So that's how we can do experiments in accelerators. Quantum theory of gravity, where you're trying to quantize gravity, that there are a number of people across the world doing it. India is one of the leaders in it. Institutions like TIFR, Institute of Mathematical Sciences, in Chennai, Harish Chandra Research Institute in Allahabad. These are all places where a number of scientists are actually working on string theory, which is a quantum theory of gravity. But there are people across the world who are doing it. They have been doing it for since the 80s, so not yet successful. There are a couple of hands here.
Yes, sir.
Yeah.
Sir, is there a possibility that because matter gathers, in the black hole due to singularity at a very dense level, is there a possibility that there is a new form of matter or antimatter which has more than 3 quarks? Is there?
Yes, yeah. So there are pentaquarks and things like that. You don't need to go near a black hole for that. Even the Large Hadron Collider and certain other particle physics experiments will generate these objects. They won't last very long. They will then they will decay very quickly. But by looking at the decay particles, you can say what was the mother particle from which they decayed.
Sir, so I have a question.
Yeah.
2, sir, actually. The first one, yes, sir.
You're somewhere here.
Yes, sir. The first one, I heard that Einstein stole the general theory of relativity from his wife. Is that true?
No. Okay. What you're referring to is the special theory of relativity, not the general theory of relativity. It is true that I believe his wife may have contributed to the special theory of relativity. There were others also who were working on similar ideas. Something called the Lorentz transformations already existed, but he gave the theory of special relativity. What is her contribution? I do not know.
And my second question, sir, if the universe is constantly expanding, does that mean we are expanding at the same rate, or?
We meaning?
Everyone, like the same things being scaled in size, or?
No, that's what I said. Gravitationally bound systems don't follow that. So the solar system is not expanding because the local gravity supersedes, is more than the average gravity of the universe, which is making things move apart. So things that are close to each other and gravitationally bound, like I'm bound to this Earth, you know, the standard gravity will, I mean, the expansion of the universe will not make an effect. But if I look at something very far away, yes, it will be moving away from me.
Hello.
Yeah.
I have two questions. One is on uncertainty principle.
On the uncertainty principle.
Yeah. So it's more about if determinism suggests a universe bound by necessity, and quantum mechanics reveals uncertainty at its core. Does this uncertainty room creates the room for free will, or it creates the room for illusion of freedom for human?
Does it create the what did you say?
Does it create the room for free will, or does it create the room for illusion of freedom?
I don't know if whether uncertainty principle determines whether you have free will or an illusion of freedom. I don't think they are linked to each other. These are two separate ideas.
But it does
uncertainty principle is not the same. I mean, free will is something else. Whether you have, whether the world is determined by God or whatever, the laws of nature completely. In that context you mean? Whether the all our actions, including the thoughts in our brain, because they're only physiochemical reactions, biochemical reactions, if it is all predetermined, I don't know whether you need the uncertainty principle there, because exactly how the brain works, I don't think people have completely figured out. There may be some, even classical random processes might be responsible for your thoughts. But maybe you may not need to invoke the uncertainty principle for that. Randomness is there also in classical physics.
And one more, it's more of how does quantum entanglement work on the cosmic scale of the structure of universe?
How does quantum entanglement work on the cosmic scale? Quantum entanglement is that if you have a system and you move things apart from each other, if you don't disturb them, even at a great distance, if you make a measurement here, it sort of determines what you will measure here, even though at this point they're far away from each other. There have been people who have been looking at coherence across cosmological length scales. There are ideas that the coherence is lost after a certain time. What might be the lead to that loss is something that is still being determined. Once galaxies, etc., form, it becomes very difficult to maintain coherence over large length scales. But even there, people have some ideas on how it could be done. Something called a Bose condensate, which exists over large distances.
Thank you.
You can decide when you want to end it. Yeah, there's a question over here. Yeah.
I wanted to ask that you said that we don't know what dark matter is, but we know what are its functions, and because of that we can predict. We could predict what happened in the past, but we don't know about dark energy, and thus we cannot predict the future. So can't the future be predicted because we know about dark matter? Can't the future be predicted because of that also?
So as I said in one of the slides, the present universe is about 68% dark energy and 27% dark matter. So dark energy is dominating today. So the evolution of the universe is dominated by properties of dark energy, which we don't know. If it was dominated by properties of dark matter, since we know many of those properties, I would be able to tell you what happens in the future.
Sir?
Yeah?
Here.
Go ahead, ask. Yeah.
Hi, sir. I can actually ask a few questions regarding the loophole theory and string theory, but I wanted to ask a very simple question, because I heard this in a documentary as well, that evolution has been happening for so long, and the universe has been expanding further on. We are expanding in many ways. But don't you think that the human consciousness and to the level that we're thinking right now is not, we are not having an evolution anymore to the level that we should have. The speed of evolution that we should have now has decreased according to, in relation with the evolution of the world, the economy, and also the universe.
On the universe timescales, existence of a planet, existence of us, hundreds of years is nothing. Okay, so what we do on this planet, how we evolve, how we think, doesn't affect, is not relevant on the larger scale. Now, within this, on this planet, how the human species has been evolving, maybe we're getting faster at certain things, we're getting slower at certain other things. We are affecting the planet in many ways. I don't know if our brains are getting faster or slower. That I don't know. I'm not a neuroscientist.
Hello, sir.
Yeah.
I wanted to know about how do we actually capture the images of galaxies and all, like just like how you showed the
How do we
example.
capture the images of galaxies?
Yes.
So we use telescopes, and we will stare at that galaxy for a long time, collect enough light from it, because the galaxy is not changing in time. I mean, not on the time scales at which we're measuring. And then we synthesize all those images and create a beautiful picture like that.
And so what if the galaxies are moving? So like, wouldn't the light
On
be
the time scale at which we are measuring, it's not moving. It's very far away. Even if it moves, you won't notice it.
Okay.
And even if it does, and then you can recalibrate that. If you can measure the speed with which it's going, you can factor that in to generate the images after, you do processing and to generate the image. And you can put that into that calculation.
So, sir, you said you were working on the very first movement of the creation of the universe. So, I wanted to know, how do you see the concept of time on the Big Bang or before it?
Time before the Big Bang, I don't know, because when you get closer to the earlier period, very early period, you need quantum gravity. Even your notion of time and how it evolves will get a little murky. So, prior to that is even worse. So, I don't know exactly what will happen at what we call 10 to the minus 43 seconds after the Big Bang, which is called the Planck time. We are not sure how time even evolves, or how to think in terms of time moving forward. We don't know. The theory doesn't exist. After that, we know how to do it. There's a question at the back there.
Thank you.
Yeah.
I wanted to ask
people
about.
in the back are also noticed. Yes, please go ahead. Yeah.
I wanted to ask about cosmic neutrino background. So you said neutrinos from the sun are something we've been able to detect. So what's the difference? Like, why is that something we could detect?
The energy at which they're traveling, the speeds, their energies are different. So I may have a detector that can detect a neutrino at a certain energy, but the cosmic neutrino background is at very low energy, and so I'm not able to detect it.
Sir, you touched upon the topic of the expansion of the universe. So I had a question related to
What
that.
do you mean touched upon? I was talking about it for an hour. Okay.
Yeah, fair. So my question was, you said that the universe's expansion is accelerating.
Yeah.
So as an expert, you must have some opinion about what happens beyond the speed of light and the observable universe. And
as an expert, I don't stick my neck out too far. What I know, or the information we have currently, the data that we have currently, does not allow us to say what exactly will happen in the future. So we wait. We have many different ideas, different models. As more data comes in, we'll be able to eliminate some models, and we'll be able to say that certain other models are plausible.
So can we predict what happens to the galaxies and stars which move beyond the observable universe, beyond our boundaries? Because
Galaxies that are out beyond our observable universe, we don't really know very much about them.
Sir, you mentioned about the center of most galaxies is black hole. So like, why don't the galaxies just like be in that one point? The black hole, why doesn't it suck the whole galaxy or something?
So why doesn't the black hole at the center of a galaxy suck up everything? There's a misconception that a black hole is like this, something that will suck up everything around it. That's not correct. Only if you get past a certain distance from the black hole will you fall in. So we, for example, are so far away from the black hole at the center of our galaxy, it barely affects us.
Okay, sir. Thank you.
I have a question.
Sure.
So, what is the law of, there's the law of conservation of mass and energy. So how does that come into relation with the expansion of the universe? So does it still follow that?
It doesn't quite. Because things are, volumes are increasing. So some of these, for example, photons lose energy because the expansion of the universe. So the laws of conservation of mass and energy get completely modified in the context of an expanding universe.
Thank you so much, sir, for such an insightful and engaging topic. Everyone was extremely curious and you solved all of their doubts.
Thank you.
On behalf of the CFP faculty and student body, we thank you for sharing your precious time with us, and thank you all for attending.
Give this back to him.
Oh, okay.
Not the mic.
Acha, no.